Okay, so good morning, everyone, and welcome to this morning's session. It's a very nice session where we will learn about the theory of planet formation and evolution, and also about different techniques to discover exoplanet. If you don't know me, I'm Ilaria Pascucci, a professor at the University of Arizona. My main focus is to understand how planets formed in the solar system and how they form around other stars, and I do that by connecting observations of disks around other stars and exoplanet demographics. So let me introduce our first speaker. This is Dr. Professor Eve Lee. She's a theoretical astrophysicist, and she's an associate professor at the University of California, San Diego, as of a few months. And given her background, she will tell us about the theory of planet formation and evolution. Yeah, take it.
I think I'll be fine with this. Oh, well, we'll check. Hello? Oh, okay. Sorry. Let's see, Zoom. It's probably hidden here. Yes. Okay, let me just make this smaller so I can find the Zoom window. Zoom window go. I can find the Zoom window. Zoom. Can you help me find the Zoom window here? I don't see it. We just had it up, right? Oh God. Yeah, it was the Zoom I can. Oh no. So this is what I just miniaturized. I don't see the. Where did the Zoom window go? Zoom window. I don't find it. Like the one with the meeting. Yeah. I just want to share desktop number 2.
We wait for the slides to come up. Maybe Eve says us something about herself, about your background.
Sure. Okay.
Can folks at the back hear me well?
That's not too.
Okay. All right. So while we are troubleshooting the technical components, as Ilaria kindly introduced me, I'm currently an associate professor in the brand new Department of Astronomy and Astrophysics at UC San Diego. Oh, I think it's up. Is it up?
Yes.
Awesome. Yeah. And as Ilaria said, I'm a theoretical astrophysicist, and I'm pleased to discuss planet formation and evolution. So because it's a brand new department, I'm going to advertise it. So I was recruited to help build this department earlier this year. So if there are any undergraduates in the audience and thinking about applying to graduate programs, do keep us in mind. We just hired 6 new faculty members, including myself. The topics include solar system, exoplanet science, among other subfields in astronomy. As part of UC, we have access to Keck Observatory, and UCSD is very well known for hosting on-site national supercomputing clusters, and there is a huge infrastructure for support. It's called Expanse. And our graduate program includes professional development courses that's separate and enhances the technical courses that are quite common in sort of nationwide curriculum. So we have a separate teaching support course, and I'm also building a new professional development course focusing on skills that would help you excel in graduate program, as well as you continue your career in and outside of academia. That's usually not often taught in typical programs. So if you're interested, that's our website, and feel free to also reach out to me directly. If you're looking for a postdoc position, we're now a 51 PEG fellow host institution. So as you apply for this opportunity, do keep us in mind as you rank order your institutions. And as part of UC, we also host UC Presidential Fellows, NASA Hubble, Sagan, and NSF Fellows as well. So why San Diego if you've never been on top of all these academic opportunities? So if you've never been to San Diego, it's only 2 hours train ride from here. It's extremely nice. It goes right along the coast. very beautiful views. And we have unbeatable weather. It's temperate year-round, goes up to maximum like mid-70s and goes down to like 60s, I believe. And the campus is right on the beach. So from the astronomy building, you just walk down like 40 minutes and you will be on the beach. And if you're not a walker, that's fine. Just take a shuttle. There's a free shuttle on campus because it's a gigantic campus. We're also on social media. So I actually managed our Instagram account at UCSD Astro. So do follow us to follow along like all the exciting things that are going on in the department. Okay, so let's now talk exoplanets. So this is cumulative counts of discovered exoplanets per discovery year. This is all public. Just go to NASA Exoplanet Archive and you can get all the updated version of this plot. So the very, very first detection of an exoplanet, I don't think it's actually on this plot for some reason, but it was made in 1988 by Canadian astronomers. And as a proud Canadian, I always make a point to point this out. So if you have not heard about it, that's probably because being the very first, it was a bit controversial at the time. And being good Canadians, they were very careful not to oversell their discoveries. So it wasn't until early 2000s where people went back to verify that indeed this really was a true planet. I believe it was actually a cold Jupiter within a binary system, so it was extra difficult. The detection that probably everyone here knows about is the one that was made in 1995 by Swiss astronomers that won the Nobel Prize in Physics in 2019. That includes Didier Queloz, who I believe gave the opening talks yesterday. So this is 51 Peg B. And there's a very important qualifier for why it merited the Nobel Prize as per their citation. It was the first detection of an exoplanet around a sun-like star. So now we're getting into like the question of, are there Earth twins out there? And like, what is the probability of finding habitable worlds out there? Although that particular planet looked nothing like what we see in our solar system. So, and I also like to point out that it's not like there were nothing in the intervening years. There were some discoveries. It's just that those discoveries were, those planets were around compact objects, so not even a star. So that's the sun-like star is the important qualifier here. Okay, so since then, we've been, the astronomers have been collecting and discovering more exoplanets. The number have been steadily growing over time. But what really revolutionized this field is the Kepler Space Telescope. And the reason for that is because it found like thousands and thousands of planets. And having that many detected exoplanets is important because now we can have the statistical strength to pick out trends and patterns and place our own solar system in the larger context. Although, as I'll show you in a bit, it's not just the fact that it found so many planets, it's the fact that it found planets that are very surprising that they exist. A bit of a personal anecdote. So I started my graduate school in 2012 at Berkeley. Before that, I was an undergraduate student at the University of Toronto. And shortly after the launch of Kepler, Toronto invited a lot of exoplanet researchers and scientists, including those who were directly involved with the Kepler mission. So as a young, naive student at the time, I got so excited looking at all this deluge of data and seeing and the speakers just pointing out like how all this data are so surprising made me think that this could be a field where even someone so young like me could make a meaningful contribution to the field. And I've been in the field ever since then. So this is, and sorry, there is a Zoom or something that's a bit cutting off, but if you load up this plot, the total number is slightly below 6,000. So you can just see sort of like a celebration of just how well we did as a community in finding so many planets. And the number continues to grow thanks to tests and all the other detection techniques that we currently use. Okay, so what do I mean when I said that the discoveries from Kepler was surprising? So pre-Kepler, This is one of the very first population synthesis models, and I believe you probably have seen like the modern version of this yesterday, and I think you will delve more into this today during the hands-on or throughout the workshop as well. But anyways, this is one of the very first. So theorists back in the days thought that we should see the rocky planets, the gas giants, and very few things in between. And then Kepler came along and found that actually most, and that's like 80% or so, of the discovered planets actually fill right in that gap. And we call them super Earths or sub-Neptunes. And we used to use those two terms interchangeably, and we now know that they're separate. But in any case, they really fill up this gap over here, and it'll look like much more obvious if you look at radius instead of mass. So the fact that this sort of upended or requires that upheaval of our prior notion of how planets form and evolve just tells us that there was like something missing in that prior theory. So the question is like, what is it? Like, what do we need to change so that we can better understand this overall population demographics? One thing you might notice if you just take a look at the overlaid observation, these are observations, you'll see that there are very few planets in this part of the diagram. Just keep in mind that that's because of detection biases. It's really hard to detect these planets, but as I'll show you in a bit, it's really important to fill up the spot if we want to understand and test different formation theories. But for now, let's focus on the short orbital distances or short orbital periods, because that's where we have most data and therefore have the best leverage. Okay, so instead of mass, we're going to take a look at radius, because we have a lot more size measurements coming from Kepler, like transit missions, as compared to independent or follow-up radial velocity at the moment. So what you're looking at is occurrence rate. That's like number of planets per stars. Think of it as a histogram as a function of size and corrected for all the detection biases. So from left to right, we're looking at small to large. Small usually means rocky. Large means gas giants. So in our solar system, we have no planets of the size between Earth and Neptune, and that gap is sort of what was also expected in that earlier population synthesis models. But as you can see, the exoplanets really fill up that region. But furthermore, it's not a flat distribution. Even at a global level, it is not a flat distribution. Our nature much prefers the formation of the small planets as compared to the large planets by at least like an order of magnitude. And if you take a look at this between Earth and Neptune, there's this really famous radius valley that a lot of people are focusing on that is separating the rocky super Earths from the more gas enveloped mini Neptunes or sub-Neptunes. I'm going to use those two terms interchangeably. And it's a relatively narrow peak because once you go beyond around 3 Earth radii, there's a cliff, and we call that the radius cliff. All right, so for the first half or 2/3 of the discussion, I'm going to focus on how we can understand why is it that the nature prefers the small planets over the large, and how we can understand these different substructures that appear in the overall population. But before I delve into the physics, because I believe these talks in this workshop is supposed to be a bit more pedagogical, let me first paint the picture of just an overall picture of how we think planets form. So planets form in what we call protoplanetary disks, which are the spinning disks of gas and dust surrounding young stars, which are the sort of leftover of star formation process. So the dust grains within this disk somehow go through multiple physical steps to coagulate into larger rocks. I'm not going to go into details of it because that merits its own completely different talk. So for this, we're just going to assume that we were able to create this massive rock because we see them. And this rock can gravitationally attract and build this planetary atmosphere. As these planets build up, the underlying disk is also evolving. So Especially at the outskirts, the gas can get blown away by the winds generated from the high energy photons from the star or by magnetohydrodynamic effects. And on the inside, the gas gets accreted onto the star. This places a time limit on planet formation. Disk gas in particular lives for about 10 million years or so. So if you'd like to form a planet with any sort of gaseous atmosphere on top, there's a time limit of about 10 million years. All right, so with that in mind, let's now get into the more detailed physics of the gas accretion so that we can understand why is it that the nature prefers the more smaller, more gas-poor planets compared to the gas giants. So again, we're going to assume that we already created massive enough rock. What is massive enough? Massive enough means that you could define the gravitational sphere of influence that is larger than the physical size of the rock itself. So the technical term for it is the minimum between the Hill and the Bondi radius. So, so what does that mean? That means that this is the sphere inside which the gas can be bound to the gravity of the core against the thermal motion and also against the tidal acceleration from the star. So that accretion process is nothing, it's a release of gravitational potential energy. So that's going to heat up the gas and create a non-zero temperature gradient, hotter here and colder there. And nature really does not like having any sort of gradient. It's the reason why when you have like a cup of coffee that's sitting in room temperature or colder climate, if that's where you're from, it cools down. So same thing here, this gas layer would like to cool down, and the gas layer that is cooling down is going to shrink. So that's going to leave some empty room so that the ambient gas from the disk can refill this gravitational sphere of influence so that the net effect of the planet building more its mass in the gaseous envelope. Okay, so that means it's really the thermodynamics. So the cooling rate, that's basically equivalent to the accretion rate of the planet. And if you want to quantify that, then we need to know the thermal structure of these envelopes. The modern picture is that there's at least 3 different thermal structures, with the outermost advective layer followed by radiative, then the deepermost convective zone. The advective layer is where the disk gas comes in and cycles out within local orbital time. Now, it turns out that outermost advective layer is thermally unimportant, and I'll describe in a bit why exactly that is the case. But because of that, for now, let's just focus on that inner radiative and convective zone. So the next thing we can ask is why that ordering? Why do we have convective zone on the inside? And it has everything to do with opacity. So remember how I said that all this cooling happens because of non-zero temperature gradient. To give you some numerical idea, it's about 10 to 20,000 Kelvin at the bottom. And at the top, it's just set by the disk local temperature. So at 0.1 AU, it's around 1,000 Kelvin. So in between, you can hit about 2,500 Kelvin. That is an important number because that's where you can thermally dissociate hydrogen molecules. So you have then the free hydrogen atoms, and you're always going to have some free electrons swimming about that got off the heavy elements. And you can make H- ions. And you can imagine how it's more likely for the H- ions to more easily lose that extra electron by absorbing photons. So H- ions become the dominant source of opacity. And again, sorry, got a bit, it's a bit covered, but if you just read off from 2,500 Kelvin, this really, really steep rise, that steep rise is the H- opacity. It's really sensitive to the temperature because like it has to do with the production of H- ions. Okay, so this means that from 2,500 Kelvin layer below, the envelope's just going to become so opaque that it becomes prohibitive to transport energy by radiation. So instead, you have convection. Another consequence, the physical consequence of hydrogen molecule dissociation is that that requires energy. So all that thermal internal energy going into populating the kinetic modes of the gas particles, it goes into dissociating hydrogen molecules. So it causes a bit of a thermostatic effect where the envelope approaches, but not actually, but approaches an isotherm. So that reduces the adiabatic gradient, and that causes a central concentration of mass. So about 80% or more of the envelope gas is all locked into this inner convective zone. And furthermore, it is centrally concentrated toward the surface of the core. Okay, so that means if I want to get sort of the bulk idea of the cooling of the entire envelope, all I need to know is the cooling rate of that inner convective zone. And for convective energy transport, what's really important is what is happening at the lid. And there's a way to show that physically, but there's also a way to show that through a pretty simple demo. I think some people in the audience have seen it if I have given this talk at your institutions. But this is a demo that I made a long time ago when I was still a grad student. This was for a donor event, but I also reenact this every time I teach a fluids class. Hopefully this can be played. Great. Okay, so what you're seeing is hot tea, and I'm pouring cream so that I can use it as a tracer of convection. And we're just gonna wait until all that sloshing of the cream to die down, because that rising motion is not convection, that's just surface gravity wave, which is sloshing. That's generated by me pouring the cream. We're gonna wait just a bit more. And what I'm gonna do is I'm putting metallic lid on top so that I can easily change the temperature at the top of this fluid mixture by putting ice cubes. So that's one. And a second. Should already see some rising. And in fact, it's able to globally sort of mix up the cream. And I couldn't see what was going on when I took this, so I put a third ice cube. And that really invigorates the overall mixing process by convection. So that within seconds, you have a full tea cream mixture just by putting ice cubes on top. So this demonstrates that for convection, what really matters is the boundary condition. And this, of course, makes sense because one of the criteria for triggering convective instability is to steepen the temperature gradient, which is exactly what I did. All right. Okay, so coming back to the exoplanet, then as long as I know the thermodynamic properties at the very top, the boundary of this convective layer, which in this case is just the radiated convective boundary, then I know how to write down the rate at which this envelope grows. And I know where this boundary happens. It happens at H2 hydrogen molecule dissociation, which happens at 2500 Kelvin. So with that insight and knowledge, we can write down completely analytically, so pen and paper calculation, how the envelope mass grows with time and varies with the core mass and elemental abundances. And just FYI, we also ran full numerical computation, and they agree extremely well. All right, so you'll note that by far it is the core mass to which the envelope mass growth is the most sensitive, and that is because of that central mass concentration. So it means that you're a lot more sensitive to the very deep interior than the outermost boundary, which is why the outer advective layer is thermally unimportant. So applying this to a wide range of the core masses and also the accretion time, this is what you get. This is the expected envelope mass fraction. All the way at the top, that is exactly covered by the little screen. It's actually half the size of the screen where the points fill up. So that's where the gas giants are. And in the middle, you have the sub-Neptunes. And for reference, there's Earth, although keep in mind that Earth atmosphere is not hydrogen helium. And as long as the envelope mass fraction goes below 10 to negative 4, 10 to negative 5, then it becomes practically rocky planets. Okay, but looking at this plot, this tells you right away that the Jupiters occupy a really tiny region of this overall parameter space, which means that the criteria for creating the Jupiter is a lot more stringent. it is very difficult to create the Jupiters compared to the smaller planets that can occur over a much wider range of the parameter space. So this just naturally gives you an idea of why is it that the nature might prefer the creation of the small planets compared to the large planets. All right, so looking more broadly at this, so you'll see that the upper envelope, sorry, you can't really see what's going on here, but it basically sort of does this. But the overall envelope here, very strong function of the core mass. The power law in between, that's given by thermodynamics that we've been discussing. And it sort of changes its behavior at the high mass end and the low mass end. So high mass end, where you create the giants, again, it switches in that it goes somewhat exponential and then it turns off. And that's because there's a transition in physics. So instead of thermodynamics, it becomes hydrodynamics dominated. And for those of you who have been in the field for a while, that's the classic runaway gas accretion, where the thermal timescale just gets really, really short, catastrophically short. So I won't talk too much about it. But at the low mass end, there's a breakoff. And that breakoff is not because there's a transition in physics, it's still thermodynamics. It's just that you have a maximally cooled. So in other words, remember all this cooling happens because of non-zero temperature gradient, but once you reach that zero temperature gradient, you're going to stop cooling and therefore you're going to stop accretion. And because it is, and that's basically an isothermal envelope, and because it's exponentially sensitive to the core mass at the low mass end, it's going to be really, really small. And that's why you have this cutoff here. And this cutoff would be a key in understanding why you may see right at the beginning this separation, this radius valley between the rocky planets and the gas envelopes of Neptunes. All right, so to see that, let me clean up the plot a bit so that we can focus on individual epochs in disk lifetime. So the same thing that we've seen before, and just notice how dramatic this drop is. If you have this dramatic of a drop, even if you have an underlying core mass distribution that is very broad, this is going to show up as a deficit in the overall population. And that's exactly what we see when we do that exercise. You get what I would call the isothermal gap. So that's the deficit of planets that would occupy these points over here. That agrees extremely well with the observed radius gap that we see in the data shown in the black dots. This radius gap or radius valley also appears in radius versus period space. There are many different versions of this plot. Sorry, got a bit cut off, but this plot comes from the Penn State group. So depending on which statistical methods you use, and also depending on which subsample you use, you can have different versions of this plot, but the shape of the radius gap is more or less the same between different groups. All right, so that's observation. Here's model. They seem to agree pretty well. And in fact, if you fit a line and compare the actual numerical slope, they agree within 1 sigma. All right, so why do you get this negative slope in the theory? So as you go closer and closer towards the star, the disk gets hotter and hotter. So it becomes more and more difficult for the given core to hold on to the more thermally energetic particles. So that means your isothermal mass is going to shrink. That will effectively shift the transition to the still cooling curve to the larger core masses and therefore larger radius of the gap at shorter orbital periods. So just to give you an idea, once you go below those are practically rocky planets, and the still cooling curve corresponds to the sub-Neptunes. All right, so from the formation perspective, in terms of the origin of this radius gap, there are other hypotheses. Again, just from the formation perspective, other hypothesis is that instead of considering sub-Neptunes as hydrogen-helium envelope, maybe they're water world. And this idea has been around for a while, I think even before I started my grad school. But it has sort of died down in fashion, but then it now has peaked up. And one of the papers that motivated this was this one. And what the authors found was when they just focus on N-dwarf planets and in radius mass space, the planets that would categorize as sub-Neptunes lie extremely cleanly and tightly along like a water world relation. So in fact, they were really arguing that how this tight mass radius relation would be more natural to be considered as water worlds, except actually turns out if you use physically correct initial conditions, you can get exact same tight relation just with hydrogen helium envelope. So there still remains degeneracy. If you just have radius, mass, and period, this degeneracy has been known for a while. But one way in which we can break this degeneracy is if we target young planets. So remember, planet formation ends at around 10 million years, but most of the planets that we observe are more like a few gigayears. So there's a pretty huge gap in time where we can like more directly infer what's going on from the formation stage to the more mature state where we can actually observe. And from the sparse data set that we currently have and growing thanks to tests right now, is that actually for these young planets, the radius distribution, there's a hint that the radius distribution might be a bit broader, a bit too broad to be explained by water worlds. But again, the data is a bit too sparse right now. So I was invited to join the NASA mission concept called EVE. Oops, we share a name. Sorry. It stands for Early Evolution Explorer, and one of the main science goals the overall science goal is to look at the early stages of the disk and planet evolution. But one of the main science goals for exoplanets is exactly this, to target specifically the young planets so that we can better understand the composition, the initial composition of these planets. Okay, so what other ways in which the planet could evolve? So again, from 10 million years to the few gigayears that we observed, there's that huge gap. So that means there are some evolutionary physics that we need to take into account. And in particular, at the short orbital periods where we have actually all the data for the small planets, we really have to be careful about the effect of interaction with the host star. So I'll discuss 3 physics that's involved with this. The first is photoevaporative mass loss that operates out to 50, maybe sometimes around 100 days, depending on the specifics of the system. And I would also like to point out that photoevaporative mass loss is actually the first theory that theorists use to predict the existence of the radius gap before the observers could really find it. Once you go a bit more closer inside like 3 days or so, then you have to worry about tidal interaction. If you go even further in, then you have to worry about magnetic interaction. So let's first talk about photoevaporative mass loss. So again, many different papers predicting the existence of the radius gap. So we're going to take our formation model that already has the radius gap and evolve it under photoevaporation. You largely get back the initial radius gap, except at the shortest orbital periods where you have more population of the small planets, which just totally makes sense. And in fact, you can corroborate that directly from the data. Again, sorry, it got cut off, or not cut off, but it got blocked. But actually, you can see the super Earth population that have the mass measurements. And if you take a look at it, that's actually way too massive. That if you want to explain the current short period super Earths with the mass measurements, they're too massive that they must have undergone photoevaporation. And again, that makes sense because when you're short in, you have a higher irradiation from the star. Photoevaporative mass loss is because of the irradiation of the X-ray and UV photons from the central star. So the closer in you are towards the star, the more likely you're going to get rid of all your envelope and transform into small rocky planets. So for someone like me who focus a bit more on the formation perspective of the planets, what I would like to do is I would like to identify a population of planets that still retain their initial memory of formation, because at this short orbital periods, you sort of erase away all that initial memory because of their interaction with the host star. So in order to be safe from that, you need to go to longer orbital periods. Unfortunately, 50 days, 100 days, like those are exactly where the current sensitivity limit dies down in the transit surveys for the small planets. So we have to look at future missions. So I'm particularly excited about two future missions. It should be near future because both of these have scheduled launch date of next year. One from NASA, the Roman Space Telescope, especially its microlensing capability, which you will hear more tomorrow, I believe. It's uniquely capable of probing down to, say, like Mars mass-ish small planets at this intermediate orbital distances. So at least we'll get a statistical idea of the population of this long period rocky planets. And if you, for reasons that do not like microlensing, then there's also European mission Plato, which I consider as a more maybe updated version of Kepler. And it's a transit mission, and as long as it can get that extended survey, then it should have access to this long period rocky planet population. So I'm really looking forward to this so that we have the ability to test the different formation theories. All right. So what about the remaining two different physics, so tides and the magnetic fields? So when we take a look at the really short orbital periods, now we're looking at like around the day or inside, we call them ultra short period planets. You can see already that they do not really, especially if you take a look at the upper envelope, it does not follow the evaporation. There's something else going on. So for that, let's take a look at tides. And I'm just going to focus on tides being raised on the star by the planet. Two important things to keep in mind. Tides, especially for the small planets, operate over multiple giga-year timescale. So stars mostly spend its time on the main sequence. At this point, the spin period is longer than the orbital period of the planet. Another thing to keep in mind, there's always some sort of unknown friction inside a star. We don't really know what it is, but it's probably the interference of the different modes that gets excited by the tidal interaction with the planet, because star is a fluid. Okay, but it's largely unknown. So because of the friction, the bulge that's raised on the star lags behind the planet and pulls on the planet that drags on the planet's orbit. So there's going to be an angular momentum transfer from the planet's orbit to the spin of the star. But remember, star is much, much, much more massive than the planet. So the star basically acts as an angular momentum bath. So the planet will just continue to spiral in until it reaches a tidal destruction zone or the Roche-Loeb radius and be destroyed instead of reaching a synchronous state. So we've been studying tides for a while. We can write down the analytic form of the orbital decay that depends very sensitively on the size of the star, because that's where the tidal bulge gets raised. And we also have this tidal quality factor where we just hide all the unknown physics of dissipation. But what I would like to show you is that looking at the small planets, we have, I think, one of the better ways to study this tidal physics that happens inside the star, especially as a function of the stellar type. And the small planets is particularly opportunistic because small planets appear over a wider range of the stellar types compared to the larger planets. So what you're looking at is the mass of the small planets versus orbital period. I've broken them down into different stellar types. The black points are the ones with good mass measurements. Magenta points are the ones without. So it'll be really, really awesome if you can get all the masses of all these planets. All right. So why is the stellar type important? Stellar type is important because depending on the type of the stars, we expect them to have different thickness of the outer convective layer, where the hotter stars to have thinner and the cooler stars to have thicker to fully convective structure. And we expect the tidal dissipation to be more efficient in the convective layer because that's where the modes decay. So we would expect stronger tidal dissipation towards cooler stars. So let's test this by integrating that orbital decay formula and looking for the region, sort of the limiting region of the parameter space where the planets can survive against the tidal decay over the system lifetime. And that's given by this red zone. So if you go over the red zone, the planets are not expected to survive. And that is in good agreement with the data for sun-like stars and K-dwarfs, but it's not doing so well for the M-dwarfs. And that's because I used, for simplicity, the exact same tidal Q parameter for all the different stars. So what this means is, if you want to bring them closer to the data, then we do require larger tidal dissipation for the cooler stars. So, so we see that there is a qualitative corroboration here, but if we want to nail this down at a more quantitative level, then we do need more mass measurements of this planet so that we can study like occurrence rates in the mass space. Okay, so tides explain the upper envelope. Now let's take a look at the left envelope. And for that, we're looking at electromagnetism. And I'm kind of getting out of time, so I'm going to go through this quickly. So the upshot is that stars have strong magnetic fields when they're young. And as planets orbit around, it plucks along the field lines. And that's going to drive waves, just like how you drive acoustic waves when you play guitar or other string instruments. And furthermore, you're going to cause a time variance in the magnetic fields. And time varying magnetic field induces electric field. And that's actually going to, in this case, draw a closed circuit loop, especially when you're this close into the star. So you basically draw a current like circuit loop with two resistors, the planet and the star. So if you have resistors in a circuit, they are going to heat up and there's an energy dissipation. And that energy dissipation leads to the orbital decay of the planet. And you can do all the calculations sort of order of magnitude level using all your Maxwell's equations and get the expression and integrate. And you can draw this boundary that agrees pretty well with the data, except for these 3 points, but those 3 points, turns out, are around slow rotators, and slow rotators are expected to have low level of magnetic field, which are in the right direction. Okay, but as in the exoplanet, as an exoplanet scientist, something that really excites me is that if you can tap into just 0.1% of this Joule heating, this energy dissipation, you can outright destroy these planets. And they could be the progenitors of catastrophically disintegrating planets that we see in the transit surveys. And if that does not happen, then it's still interesting because the amount of heat generation, heat flux, is comparable to what is currently driving volcanism on Io. So these planets could be ideal targets to study exoplanetary volcanism. And the really cool thing about this is that this volcanism would happen on the night side as well, not just on the day side that a lot of people talk about when they discuss lava planets. All right, so to summarize, the farther out you go, the more likely you're probing formation history, especially if you can probe the small planets beyond 100 days of orbital period, then you're really probing the initial conditions. And also, it's important to probe and target these younger systems. And when I say younger, I mean like less than 100 million years, because they would be best positioned to distinguish between hydrogen helium versus the water world. That's the more dominant composition of the sub-Neptunes. At short orbital periods, you're more likely probing the star-planet interaction rather than formation because all that history is erased at that point. So at ultra short periods, if we can get more mass measurements, then I think we have a really good chance to study more detailed stellar mass-dependent tidal physics. And finally, at even short orbital periods and for even lower mass planets, there is a chance of magnetic volcanism. And this could be a good target to get the optical spectra for refractory species or even JWST spectra if we think that they're volatile species that's locked inside. Thank you.
So thank you very much, Yves, for this very nice talk and very informative. We have only time for 2 questions, I'm told, because we are running out of time. So just 2 quick questions from the audience. Let's start here. There is one online? Okay, so please go ahead.
What about giant planet formation via gravitational instability?
Yeah, so gravitational instability, it's more likely to occur at the wide orbital separation. So they could be relevant for like more massive, like directly imaged planets, not at these orbital periods.
Any questions? Oh, yes. Oh, you have the microphone there. Go ahead. You can push the button.
All right. Thank you. Yeah. Great talk. What about like other kind of like mass loss effects, like core powered mass loss that kind of happens as a kind of independent of like orbital separation?
Yeah, so core power mass loss is actually dependent on the orbital separations, and that's because like the energy itself is coming from on the inside, but the rate at which you lose that mass is actually given by the bolometric temperature, because like you're initiating the mass loss at the sonic radius. So it actually depends on equilibrium temperature. So it actually depends on the very similar and almost like the same way as the photoevaporation in terms of just like the shape of the radius gap, for example. About the core powered mass loss, so the initial theory focused on the energetics, and very often you do have enough energy, the internal energy, to drive off that mass loss. But turns out if you're a bit more careful about the internal structure, it does not happen, because what's really relevant is the luminosity, not the power, not the energy. So the more modern sort of like in the last year or so, papers have been arguing that it's probably more likely photoevaporation than core power mass loss.
Okay, thank you very much. Let's thank Yves